semicon. So from this module, we'll discuss the things related to complete synthesis. What is meant by synthesis and what is the role is played in the physical design flow. Okay, so we'll discuss all these things in particular synthesis module. Let me share my screen. Okay, I hope my screen is visible. Right, so here we'll discuss the things related to some basics of synthesis. What is mean by synthesis actually? So let me recall the things we are having. Flow, right? First, system specifications. After that, RTL code, right? After that, we are having synthesis. After synthesis, we are moving to physical design, which means from here we are having floor planning, placement, and all the things. Okay, so here is the step is known as synthesis. So okay, so what is this particular step is going to be performed in this complete ASIC flow and all we'll discuss. So in this particular RTL code, so when you are having one indicate means, okay, one indicate logic, A and B as inputs and Y is the output. Then in this RTL step, we'll write the complete RTL code. What are the inputs of this particular gate and how this AND gate is going to be performed and all. We'll write the complete code in this RTL step. But after RTL, we are having one step called as synthesis. So in this synthesis step, so this complete RTL code, whatever there in the RTL code, which means whatever the logic, that complete logic here, this is the logic, right? For this AND gate, we'll write some logic as Y is equal to A and B, correct? So we'll write the code in Verilog or HDL format in RTL code. So that RTL code, that logic is completely translating into gate level netlist. Okay, netlist file. I'll explain what is mean by netlist file, what is mean by gate level netlist and all. Okay, so this complete RTL logic is translating into a netlist, and this netlist is we are given to the physical design step. Okay, this is the major step. Netlist is the major input. Okay, so netlist is the major one of the input to the physical design people. Okay, this netlist file is generated by this synthesis step. Okay, what is mean by synthesis? Means synthesis is the process of translating this RTL code into a gate level netlist. Understand? So that is the thing. So what is mean by logical synthesis, right? So definition, here is the definition. Logic synthesis is the process of converting, which means translating. What we are translating here, we are translating the RTL, which means register transfer level or logic, which means whatever there in the Verilog format or VHDL format, we are having one logic means for that logic we'll write the code in Verilog or HDL formats, right? So that RTL description is translating, is converting into a gate level netlist. Okay, clear? So this is the thing. I'll explain what is mean by gate level netlist and all. Okay, so for this logical synthesis, we need one input. That input is HDL code written in the code, whatever there the logic. Okay, so I'll explain, right? We are having one AND gate and all. So for that particular specifications, we are having some logic. Okay, that logic is in the form of Verilog or else VHDL describing the circuit behavior, which means it describing the circuit behavior. What are the inputs, what are the outputs, and how a circuit is going to be work and all. So all the things is we write in this Verilog or VHDL format, right? So that is the major input for the synthesis people. So after synthesis, we are translating this RTL code into a gate level netlist. right? So then what is the output of the synthesis file? A gate level netlist mapped to technology library cells. Wait, so for this particular gate, this is the end gate, and this end gate having a and b inputs, and y is the output. Okay, so we are writing the logic in Verilog or VHDL format, that is fine, but same logic is there in my VHDL RTL file and netlist file. Both the things are same. There is no change in the logic, same inputs, same outputs. But the major thing was it translating into a gate level netlist, which means which technology it is depending on. The gate is depending on which type of technology, which means this is AND gate. In the AND gate also we are having different things, right? This AND gate having two inputs means this is the two input AND gate. Okay, like that. Which type of AND gate we are using, on which technology my AND gate is depending on, what is the drive strength of this AND gate, what is the input transition, what is the output transition of this AND gate, that complete physical information of particular cells. Okay, so up to RTL file we are having only logic of this particular AND gate, but in technology mapping, this gate level netlist contains the complete physical information of this particular AND gate. Understand? So that is the major difference between RTL code and a netlist file. Okay, so in RTL code we are write the logic only, right? So same logic is there in the netlist file, but what is the chain here? We are mentioning the which type of AND gate we are using, on which technology it is depending on, what is the input transition, output transition, and all. So what is the drive strength? So complete physical information of the particular circuit, okay, that is there in this gate level netlist file. Okay, so for doing this particular logical synthesis, we are using one tool called as, here we are having one tool, that tool is design compiler. So we are having different things, like for synopsis we are having synopsis tools. By using synopsis tools also we can do, or else by using cadence tools also we can do. Okay, so here for synopsis tool, we are using one tool called as design compiler. So by using this design compiler, we'll translate the RTL code into a netlist file, which means synthesis. By synopsis people will done the synthesis in design compiler. Understand? So this is the thing. What is the major purpose? So what is the major purpose of synthesis means? It bridges the gap between the designer intent and physical implementation. Okay. So up to RTL code, we are having the design logic, right? So it acts as the bridge between, synthesis is the acts as the bridge between that logic into a logic to the physical implementation of the particular circuits. Understand? So this is the thing. So this is the some RTL to gate level flow, how we are going to be and all. So first thing was RTL or HDL codes will done the logic, will write the logic in RTL or VHDL language, right? So for tools, which type of tool here we are using? Here we are using synopsis tool, that is design compiler DC. Okay, DC cell we are using for synthesis process. So after that we are generating one gate level netlist file. So here generic boolean netlist. Okay, so we are translating this RTL code into a particular netlist, which means I said you right, which type of AND gate, either two input AND gate, three input AND gate, and what is the drive strength of that particular AND gate, all the things. Okay, so after the technology mapped netlist, which means completely, by netlist is completely dependent on technology, which means depending on the technology, drive strengths and input transitions, output transition may varies. Okay, that's why this netlist is completely dependent on technology. So here this is the major output. It creates a technology mapped netlist, which means gate level netlist. Okay, so this is the thing. First we are having RTL. RTL by using this compilation methods. Compilation means in after the compilation step we'll get the technology map netlist. Okay, so this is the thing. Clear? So why synthesis is important? Okay, so synthesis is mainly important for optimization of area, optimization of time. Okay, so on optimization of power also I'll explain how and all. So this is mainly used for automation. Manual gate level design is error prone and slow for complex chips. Are we are having one RTL code, right? So when we are using that particular RTL code, so we are having some delays or else some issues in the file, RTL file. So to overcome all those issues, we are using synthesis for automation purpose also. Okay. So by using this synthesis, we can get the particular gate level netlist design. Okay. So after that, optimization also occur. So synthesis tool optimizes for area, speed, and power. Right. So how it will be means we are using one AND gate means so is we are having only two input and we are having only A and B as inputs, but we are using four input AND gate. So I am having only in my design I'm having only A and B is my inputs, but I'm using tool unfortunately adding some four input AND gate. So sorry, let us assume this one as the AND gate. Okay, so this is my four input AND gate. Okay, but here I'm using only two inputs and remaining two inputs are I grounded. Okay, so this one also correct. There is no change in the logic, but what is happening here? It will take more area and it will consume more power also. Why? Because my drive strength also increases. Why? Here we are having more inputs, which means more load it will take, right? So to think all these concerns and all, so in synthesis process, it will do the complete optimization for particular area, speed and power automatically. So while doing the synthesis process, it will do all the things, and same RTL can be synthesized for different process nodes. So when we are having one RTL code means that RTL code is used for any technology. Why? Because that is independent of technology, but netlist file won't be. Endukante? Why? Because netlist file is completely dependent on the technology. Why? Here in netlist file we are having the complete physical information, right? So that is the thing. And synthesize and netlist use it for formal verification and gate level simulations. So for complexity issues, modern SOCs have billions of gate. So in synthesis is the only flexible approach, which means we are having billions of gates. So when we are facing all these issues, this is the one of my minor issue. So in this, when we are implementing the design, we may throw so many errors. So to overcome all those issues, we are fixing all these issues in this particular synthesis step. Okay, so because of that reason, the area may be minimizes, speed also minimizes and power also minimizes. Okay, and these are the primary goals of synthesis. Okay, so minimize critical path delay. So when we are having two flip-flops means, okay, so for this particular flip-flops one clock port is there. Okay, we are applying some clock. So for every flip-flop we are giving the clock, right? So when we are adding the clocks to a particular flops, our duty is to as much as minimize the path delays, which means path delay means from this clock port to from this particular flop how much delay it will take, which means how much time it will consume. Okay, so to do all the things and meet setup and whole timing constraints, I'll explain what is mean by and what is mean by hold setup and hold things in further slides. Okay, and we need to minimize the operating frequency. When my operating frequency is less, then we are having more time, right? Frequency f is equal to 1 by t. You all know this point, right? Frequency means 1 by t timing, right? When we are minimizing the frequency, obviously we can get more timing to achieve the complete data, right? And optimize clock to q paths, and this is the thing, is the from clock to q we need to minimize the path, we need to optimize the path, okay, for faster distribution and all. And for area and power concerns also, minimize cell count and routing, we need to minimize the cell count. So instead of adding two cells for same logic, okay, we are avoiding to use particular more cells, or we are using we need to minimize the cell count also and particular routing also. So we are having these two flops, means this is the one of the path, and or else this is also one of the path for this particular flip flop, but this path we cannot do. Why? So because of this it may throw so many errors, like my route here, my routing increases, right? Routing means wire length, wire length increases. When my wire length increases, then obviously timing also increases. So we need to minimize as much as possible, okay, routing also, and reduce dynamic switching power. So when we are giving the power, then only it will transfer the logic, right? So we need to minimize the switching power also, right? So how we can reduce that one? So depending on the input transitions, okay, so when my input is transition from 0 to 1, or 1 to 0, then it will consume some power, right? So depending on all these concerns, we need to minimize the power also, and we need to minimize the current also, leakage currents and all, okay. So these are the main inputs to perform synthesis. First one is RTL file, obviously correct. So this is the major input, right? RTL file for the synthesis. So in this we are having complete Verilog and VHDL format file. It describes the design behavior, right? So after that we are having another file called as target technology library. So in this file we are having the complete cell modules with timing, power, and data, which means complete physical information of the particular cells. Okay, so after that, link library. Sorry. So when we are using one cell in the design, we are using one of the cell, okay, to design my logic. Then so for this particular cell, the behavior of the cell is present in this link library, which means we are not linked the library, then it will throw the errors as unresolved references, which means we are using the particular cell, but the tool won't know what is the behavior of that particular cell or not. When we are mentioning, when we are linking the library, then only it will resolve the references, and the tool also knows the complete behavior of the cell also, right? Understand? So after that, SDC, synopsis design constraints. So in this particular input file we are having the complete information of clocks, which means how we are creating the clocks, what is the input transition, output transition of the clock, and false paths, okay, and we are having multi-cycle paths and all these things, okay. Complete clock related things are there in this synopsis design constraint file, okay. And we are using TCL code to automate our design, right? So this is the thing we are using. 1 minute, okay. So after doing synthesis, these are the outputs we can get. First one is netlist file. This is the major thing, right? Complete our RTL file is translating into a gate level netlist. So dot v is the extension, and design database dot ddc, which means but in this particular design database file, sorry, what we are doing are complete information of the design, which means up to now we are translating the RTL file into netlist file, right? So how this process is going to be involves, and each and every point is present in this .ddc file. Okay, so it's storing the complete design state, which means it stores the complete. So up to now we are using, we are done up to the some we are having some things like analyze, elaborate, and compile things. So in the analyze step, we are analyzing the design, and in the elaborate step, analyzing means we are checking for is there any errors or not. We'll check, and after that we are having another step called as elaborate. So in this elaborate step, we are translating the complete RTL. This RTL code is translating into a gate level netlist, right? So up to now we'll done only the analyze step. Okay, so due to some works and all, we'll close the work, and in the tomorrow session we'll do the thing related to elaborate. So the design, so up to the analyze step, okay, whatever the data is there, that data is stored into this .ddc, which means current state, up to which state we are done the process, it will store the data. Understand? After that we are having some timing reports also related to setup, hold, and timing paths, complete timing violations, worst timing path, total negative slacks, worst negative slacks, complete errors and issues related to complete timing also we can get. Okay, and area reports also. Okay, so how many cells we are using to design the particular logic, and how many combinational cells are there, how many sequential cells are there. Okay, by using how many cells we are design the logic, that complete information is present in this area report and power report also. In the power report we are having dynamic power consumption and static power consumption, all the complete power intent information is there in this power particular power report file. Okay, and constraints file, this is the thing related to complete timing also. I'll explain in the previous slide, right, what is mean by SDCs and all, right? So that is the thing, and we are having different types of synthesis optimization. Okay, so when we are doing the synthesis, I said you right, we are doing for optimization purpose. So these are the different kinds of optimization. First one is combinational logic optimization, which means we are having one AND gate. Okay, for this AND gate, A and B are the inputs and Y is the output. Okay, so what is the behavior of the AND gate? When both my inputs are 1, then only we can get the output as 1. Okay, so for this particular AND gate, my B input is grounded, which means 0. Okay, and we are having only one of the input A. Okay, then always we are getting the output as 0. Okay, then what is the need of this AND gate? Here there is no need, right? So even though I am getting 0 also, we can get the output as 0. Even though I am getting 1 also, we are getting the output as 0. So there is no prior use of this AND gate, right? Why? Because one of the input as 0, so whichever the input is, we can get the output as always 0. Then at this time we remove this AND gate and we are changing it to a complete 0 cell, which means we are giving the tie low cell. We are having different cells, physical implementation cells. So for this particular case we are using the, always we are giving the 0. Okay, so this is the thing. So these types of issues are resolved or optimized in this particular combinational logic. Okay, boolean minimization, and we are having one expression called, and by using some minimization steps and all, we need to minimize the logic as much as possible. Okay, so after the sequential optimization and data path optimization, which means our data path should be as minimized as much as possible, because for this particular path only we are transferring the data, right? So we need to minimize it. If the path is minimized, it means then we can fastly transfer the data. right? And we are having MCMM means multi-corner multi-mode. So for this particular case, we are checking the complete design, complete logic. We are having billions or millions of cells in our design, right? So for this, all the particular cells we are checking are designed in different modes and different corners. Okay, we are checking for worst case analysis. Okay, if we are doing for worst case analysis, if my worst case is perfect, then obviously my best case is obviously perfect, right? That's why we are checking for worst case analysis in sorry, multi corner and multi mode step. So this is the thing, and this is the major difference between one synthesized and non-synthesized, which means this is the Verilog file and this is the netlist file. Sorry, this is the netlist file and this is the Verilog file. Okay. And after that, these are the steps, technology mapping, how is going to be happen and all. So generic optimization means I'll explain you, right. We need to minimize the logic. So that thing is happening in a generic optimization step, and mapping, which means generic gates are replaced with cells from the target technology library. So depending on the technology, so we can replace our logic into particular technology gates. Okay, and cell selection, which means which type of I'll explain you, right, which for particular end gate, which type of end gate we are using, what is the drive strength, best drive strength of that particular cell, and what is the which type of voltage cell it was, it will take high VT or low VT. So complete things related to technology. Okay, so here we are having one thing called as high VT and low VT. So which means VT means threshold voltage, right? So threshold voltage means after that threshold voltage, a transistor is going to be work, correct? So when we are having low VT cells, the cell is always high speed, which means with the less amount of VT, we can switch on the transistor, which means we can fastly switching on the transistor with low amount of voltage. At this time, what happened? My speed is increases as compared to high VT cells. So high VT cells are starts working when we are getting the maximum amount of the voltage. So when we are getting the maximum amount, which means more voltage, then only we can switch on the transistor. Then what happened? My speed is decreases, right? But it will take low power. Why? Because it will take more time to switch on the transistor. So that is the reason. Okay, so for this particular low VT cells, there is a more leakage currents also, right? So why my speed is increases, so it may not concern about the power things. Okay, so this is the thing, and these are the gate level netlist, how he is going to be behave and all. Okay, some module declaration, wire declaration, cell instantiation, okay, port connections, and so all these things is related to code. Okay, so in this, see, check here. So when in a particular RTL code, we are having only end gate name, but for this we are having particular drive strength and input pins also. Okay, so and these are the net names, which type of net we are using, and name of the net, all the things is present in gate level netlist file. Okay, so these are the different compilation step. Generally, all uses this compilation. This is the standard compilation method. Okay, so this is for normal process. Okay, and after that we are having compile ultra. It is more aggressive than this compile. Okay, after that we are having compile ultra scan. And what is the need of this scan mode means? So our design is divided into different chains. Okay, so we are checking the output for each end of the chain. Is there any errors? At that time it will rectify the errors. Okay, so this is the compile ultra scan and incremental compile and area effort and map effort. These are the things when we are doing the compilation process. Okay, so timing concepts. So these are the some of the timing terminologies. So setup time, hold time. Okay, so this is the clock. 0 1 and 0 1 and 0. Okay, so this is the rise time, fall time, rise time and fall time. What is mean by setup means, so whenever my data is, my cycle is one, then only it will transfer the data, right? So this is the complete one cycle from positive edge to positive edge. This is the one cycle, correct? So my data should be stable before the rising edge of the clock. Okay, my data should be stable before rising of this positive edge. So for this particular one cycle, my data should be stable before the rising edge of the clock. So if my data is stable before this particular margin, then whenever my signal is triggered to 1, then it can easily transfer the data to the next cycle. If my data is not stable until this margin means, then it may face some issues while transferring the data from one cycle to the next cycle, correct? So that's why in setup time we need to stable the data before rising edge of the clock, right? So this is the thing, data must be stable before clock edge, and whole time data must be remain stable after the clock edge. Okay, so here we are having hold edge. So after the window my data should be stable, whatever the data is coming from previous cycle. So after this particular window my data should be stable. Okay, so with this is the timing window, this is the hold margin and setup margin. So in between that we are having timing window. So within the timing window my data should be stable. So here we are checking for hold, and here we are checking for setup, understand? And after that we are having a terminology called slack. So slack means when we are having two flops. Okay, so this is the clock and here also this is the clock. Okay, so from this data is coming like this. Okay, so slack means this is the launch flip-flop, which means here we are launching the data and here we are capturing the data, whatever the data is sending from the flop. Okay, so these are from this register to this register, from this flop to this flop we are sending the data. So here we are launching the data, then launching the data is captured for this particular flop. So how much time it will take to travel from launch flop to capture flop, that is known as slack, which means required time minus arrival time. So required time means how much time it will require, so arrival time means within which time it will erase the data. So to know the data, okay, so how much time it will take from this launch flop to capture flop, the data is known as slack. So we are having positive slack and negative slack. Positive slack, sorry, positive slack means within the required time my data is arrived before, right? Then only we'll get the slack as positive, right? So my required time is 20, let us think. Okay, so within 20 seconds my data should be stable to this, my data is captured at this capture flop. But within the time, within 18 seconds my data is completely captured. So in this time what happened, we are having extra time also having +2, correct? So this is known as positive slack. So we are having required time only 20 seconds, but it will take 22 seconds to transfer the data. So at this time what happened, -2, which means this is the negative slack, which means it leads to violation. If my data is violated, then obviously it will affect to the next cycle, right? So this is the thing. And critical path means longest combinational path. So if we are having longest path, which means we are having more routing on that particular path, we can see more delays and all. Okay, and clock period, so clock period means We are giving the particular period to the clock, which means on which when we are transferring the data from 0 to 1, how much time it will take to transferring the data for particular cycle. So in this we are mentioning the clock period stage. Okay, these are the some of the timing terminologies. And common synthesis, some of the issues when we are doing the synthesis, these are the things. And the missing constraints, which means forgot to mention the clock names and clock input delays, clock output delays, which means all these things are we are given in SDC file, right? Synopsis design constraints file. So when we are forgot to give the input delays, output delays, and transition times of the particular paths, it will throw the error as some missing constraints and all. And latch from incomplete if case without default, which means we write the logic some if case and we forgot to close the case and all, then also it will throw error. And combinational loops. Okay, feedback without registers, we are using one flops, but there is no use of that flop, which means we are not giving any, there is no input for this particular flops and all. At that time will it will throw the error as combinational loops and some unconstrained inputs also. So these are the some of the issues while we are doing the synthesis process. Okay, so after that we are having, these are the quality of timing results. Okay, QR results. So synthesis reports, worst negative slack, total negative slack. Worst negative slack means this is the most critical path, most critical timing violation in our design. Okay, so as coming to this total negative, and so these are the total negative slack, which means it will sum of all negative slack. So in worst negative slack we can get one negative slack result, right? So by combining all the slacks we'll get one slack called as total negative slack. And area issues and power issues. So sorry, so in the quality of results we can get all these things. And these are the things. So we'll discuss the things related to some of the input files and what is meant by synthesis, and how a how a artist file is RTL file is translating into particular gate level netlist and all. And some of the QR results and synthesized files and some of the optimization techniques. Okay, so that is the thing related to basics of synthesis. That's it for today. Thank you.